Chapter 22 of Astronomy, The Science of the Heavenly Bodies, by David Todd. Chapter 22, Mountain Observatories. The century that has elapsed since the time of Sir William Herschel, known as the father of the new or descriptive astronomy, has witnessed all the advances of science that have been made possible by adopting the photographic method of making the record instead of depending upon the human eye. Only one eye can be looking at the eyepiece at a time. The photograph can be studied by 1,000 eyes. At mountain elevation, telescopes are now extensively employed, and there the camera is of especial and additional value because the photograph taken on the mountain can be brought down for the expert to study at ease and in the comfort of a lower elevation. We shall next trace the movement that has led the astronomer to seek the summits of mountains for his observatories, and the photographer to follow him. Not only did the genius of Newton discover the law of universal gravitation and make the first experiments in optics essential to the invention of the spectroscope, but he was the real originator also of the modern movement for the occupation of mountain elevations for astronomical observatories. His keen mind followed a ray of light all the way from its celestial source to the eye of the observer and analyzed the causes of indistinct and imperfect vision. Endeavoring to improve on the telescope as Galileo and his followers had left it, he found such inherent difficulties in glass itself that he abandoned the refracting type of telescope for the reflector, to the construction of which he devoted many years. But he soon found out what every astronomer and optician knew to their keen regret, that a telescope, no matter how perfectly the skill of the optician's hand may make it, cannot perform perfectly unless it has an optically perfect atmosphere to look through. So Newton conceived the idea of a mountain observatory, on the summit of which, as he thought, the air would not only be cloudless, but so steady and equable that the rays of light from the heavenly bodies might reach the eye undisturbed by atmospheric tremors and quiverings, which are almost always present in the lower strata of the great ocean of air that surrounds our planet. This is the way Newton puts the question in his treatise on optics. He says, "The air through which we look upon the stars is in perpetual tremor, as may be seen by the tremulous motion of shadows cast from high towers and by the twinkling of the fixed stars. The only remedy is a most serene and quiet air, such as may perhaps be found on the tops of the highest mountains above the grosser clouds." Newton's suggestion is that the highest mountains may afford the best conditions for tranquility, and it is an interesting coincidence that the summits of the highest mountains, about 30,000 feet in elevation, are at about the same level where the turbulence of the atmosphere most likely ceases, according to the indications of recent meteorological research. These heights are far above any elevations permanently occupied as yet, but a good beginning has been made and results of great value have already been reached. Curiously, investigation of mountain peaks and their suitability for this purpose was not undertaken till nearly 2 centuries after Newton, when Piazzi Smythe in 1856 organized his expedition to the summit of a mountain of quite moderate elevation and published his Tenerife, an Astronomer's Experiment. Tenerife is an accessible peak of about 10,000 feet on an island of the Canaries off the African coast, where Smythe fancied that the conditions of equability would exist, and on reaching the summit with his apparatus and spending a few days and nights there, he was not disappointed. Could he have reached an elevation of 13,000 feet, he would have had fully 1/3 of all the atmosphere in weight below him, and that the most turbulent portion of all. Nevertheless, the gain in steadiness of the atmosphere providing better seeing, as the astronomer's expression is, even at 10,000 feet, was most encouraging, and led to attempts on other peaks by other astronomers, a few of whom we shall mention. Davidson, an observer of the United States Coast Survey with a broad experience of many years in mountain observing, investigated the summit of the Sierra Nevada mountains as early as 1872 at an elevation of 7,200 feet. His special object was to make an accurate comparison between elevated stations at different heights. He found the seeing excellent, especially on the sun, but the excessive snowfall at his station, 45 feet annually, was a condition very adverse to permanent occupation. In the summer of 1872, Young spent several weeks at Sherman, Wyoming, at an elevation exceeding 8,300 feet. He carried with him the 9.4-inch telescope of Dartmouth College, where he was then professor, and this was the first expedition on which a large glass was used by a very skillful observer at great elevation. He found the number of good days and nights small, but the sky was exceedingly favorable when clear. Many seventh magnitude stars could be detected with the naked eye. Young's observations at Sherman were mainly spectroscopic, however, and they demonstrated the immense advantage of a high-level station far above the dust and haze of the lower atmosphere. He pronounced the 9.4-inch glass at 8,000 feet the full equivalent of a 12-inch at sea level. Mont Blanc, of 15,000 feet elevation, was another summit where the veteran Janssen of Paris maintained a station for many years, but the continental conditions of atmospheric moisture and circulation were not favorable on the whole. Janssen was mainly interested in the sun, and the daylight seeing is rarely benefited owing to the strong upward currents of warm air set in motion by the sun itself. Mountains in the beautiful climate of California were among the earliest investigated, and when, in 1874, the trustees of Mr. James Lick's estate were charged with equipping an observatory with the most powerful telescope in existence, they wisely located on the summit of Mount Hamilton. It is 4,300 feet above sea level, and Burnham and other astronomers made critical tests of the steadiness of vision there by observing double stars, which afford perhaps the best means of comparing the optical quality of the atmosphere of one region with another. The writer was fortunate in having charge of the observations of the transit of Venus in 1882 on the mountain, when the observatory was in process of construction, and the quality of the photographs obtained on that occasion demonstrated anew the excellence of the sight. Particularly at night, for about 9 months of the year, the seeing is exceptionally good, especially when fog banks rolling in from the Pacific cover the valleys below like a blanket, preventing harmful radiation from the soil below. The great telescope mounted in 1888, a 36-inch refractor by Alvan Clark, has fulfilled every expectation of its projectors and justified the selection of the site in every particular. The elevation, although moderate, is still high enough to secure very marked advantage in clearness and steadiness of the air, and at the same time not so high that the health and activities of the observers are appreciably affected by the thinner air of the summit. This telescope is known the world over for the monumental contributions to science made by the able astronomers who have worked with it, among them Barnard, who discovered the fifth satellite of Jupiter in 1892, Burnham, Hussey, and Aitken, who have discovered and measured thousands of close double stars, Keeler, who spent many faithful years on the summit, and Campbell, the present director, whose spectroscopic researches on stellar movements have added greatly to our knowledge of the structure of the universe. Among the many lines of research now in progress at the Lick Observatory and in the D.O. Mills Observatory at Santiago, Chile, are the discoveries of stars whose velocities in space are not constant but variable with the spectral type of the star. Mr. Lick's bequest for the observatory was about $700,000. So ably has this scientific trust been administered that he might have well endowed it with his entire estate, exceeding $4 million. Another California mountain that was early investigated is Mount Whitney. Its summit elevation is nearly 15,000 feet, and in 1881 Langley made its ascent for the purpose of measuring the solar constant. He found conditions much more favorable than on Mount Etna, Sicily, elevation about 10,000 feet, which he had visited the year before. But the height of Mount Whitney was such as to occasion him much inconvenience from mountain sickness, an ailment which is most distressing and due partly to lack of oxygen and partly to mere diminution of mechanical pressure. Mount Whitney was also visited many years after by Campbell for investigating the spectrum of Mars in comparison with that of the Moon. Langley found on Mount Whitney an excellent station lower down at about 12,000 feet elevation, and by equipping the two stations with like apparatus for measuring the solar heat, he obtained very important data on the selective absorption of the atmosphere. Returning from the transit of Venus in 1882, Copeland of Edinburgh visited several sites in the Andes of Peru, ascending on the railway from Molendo. Vincocaya was one of the highest, something over 14,000 feet elevation. His report was most enthusiastic, not only as to clearness and transparency of the atmosphere, but also as to its steadiness, which, for planetary and double star observations, is almost as important. Copeland's investigation of this region of the Andes has led many other astronomers to make critical tests in the same general region. Climatic conditions are particularly favorable, and the sites for high-level research are among the best known, the atmosphere being not only clear a large part of the year, but in certain favored spots exceedingly steady. In 1887, the writer ascended the summit of Fujiyama, Japan, 12,400 feet elevation. The early September conditions as to steadiness of atmosphere were extraordinarily fine, but the mountain is covered by cloud many months in each year. There is a saddle on the inside of the crater that would form an ideal location for a high-level observatory. This expedition was undertaken at the request of the late Professor Pickering, director of Harvard College Observatory, which had recently received a bequest from Uriah A. Boyden amounting to nearly $250,000 to establish and maintain in conjunction with others an astronomical observatory on some mountain peak. Great elevations were systematically investigated in Colorado and California, the Chilean desert of Atacama was visited, and a temporary station established at Chosica, Peru, elevation about 5,000 feet. Atmospheric conditions becoming unfavorable, a permanent station was established in 1891 at Arequipa, Peru, elevation 8,000 feet, which has been maintained as an annex to the Harvard Observatory ever since. The cloud conditions have been on the whole less favorable than was expected, but the steadiness of the air has been very satisfactory, in addition to planetary researches conducted there in the earlier years by W. H. Pickering. Many large programs of stellar research have been executed, especially relating to the magnitudes and spectra of the stars. In conjunction with the home observatory in the Northern Hemisphere, this afforded a vast advantage in embracing all the stars of the entire heavens on a scale not attempted elsewhere. The Bruce Photographic Telescope of 24-inch aperture has been employed for many years at Arequipa, and with it the plates were taken which enabled Pickering to discover the 9th satellite of Saturn, Phoebe, and the splendid photographs of southern globular clusters in which Bailey has found numerous variable stars of very short periods, very faint objects, but nonetheless interesting and of much significance in modern study of the evolution and structure of the stellar universe. The crowning research of the observatory is the Henry Draper Catalogue of Stellar Spectra, now in process of publication, which is of the first order of importance in statistical studies of stellar distribution with reference to spectral type, and in studying the relation of parallax and distance, proper motion, radial velocity, and its variation to the spectral characteristics of the stars. Perrine of Cordova is now establishing on Sierra Chica, about 25 miles southwest of Cordova, a great reflecting telescope comparable in size with the instruments of the Northern Hemisphere for investigation of the southern nebulae and clusters and motions of the stars. The elevation of this new Argentine observatory will be 4,000 feet above sea level. Another observatory at mountain elevation and in a highly favorable climate is the Lowell Observatory, located at about 7,000 feet elevation at Flagstaff, Arizona. Many localities were visited and the atmosphere tested, especially for steadiness, an optical quality very essential for research on the planetary surfaces. Mexico was one of these stations, but local air currents and changes of temperature there were such that good seeing was far from prevalent, as had been expected. At Flagstaff, on the other hand, conditions have been pretty uniformly good, and an enormous amount of work on the planet Mars has been accumulated and published. The first successful photographs of this planet were taken there in 1905, and Jupiter, Saturn, the zodiacal light, and many other test objects have been photographed, which demonstrates the excellence of the site for astronomical research. Within recent years, spectrum research by Slipher, especially on the nebulae, has been added to the program, and the rotation and radial velocities of many nebulae have been determined. On Mount Wilson near Pasadena, California, at an elevation of nearly 6,000 feet, is the Carnegie Solar Observatory, founded and equipped under the direction of Professor George E. Hale as a department of the Carnegie Institution of Washington, of which Dr. John Campbell Merriam is president. The climatology of the region was carefully investigated, and tests of the seeing made by Hussey and others. Although equipped primarily for study of the sun, the program of the observatory has been widely amplified to include the stars and nebulae. The instrumental equipment is unique in many respects. To avoid the harmful effect of unsteadiness of air strata close to the ground, a tower 150 feet high was erected, with a dome surmounting it and covering a chelostat with mirror for reflecting the sun's rays vertically downward. Underneath the tower, a dry well was excavated to a depth equal to 1/2 the height of the tower above it. In the subterranean chamber is the spectroheliograph of exceptional size and power. The sun's original image is nearly 17 inches in diameter on the plate, and the solar chromosphere and prominences, together with the photosphere and faculae, are all recorded by monochromatic light. Connected with the observatory on Mount Wilson are the laboratories, offices, and instrument shops in Pasadena, 16 miles distant, where the remarkable apparatus for use on the mountain is constructed. A reflecting telescope with silver-on-glass mirror 60 inches in diameter was first built by Ritchie and thoroughly tested by stellar photographs. Also, the northern spiral nebulae were photographed, exhibiting an extraordinary wealth of detail in apparent star formation. The success of this instrument paved the way for one similar in design, but with a mirror 100 inches in diameter, provided by gift of the late John D. Hooker of Los Angeles. The telescope was completed in 1919. Notwithstanding its huge size and enormous weight, the mounting is very successful, as well as the mirror. Mercurial bearings counterbalance the weight of the polar axis in large part. This great telescope, by far the largest and most powerful ever constructed, is now employed on a program of research in which its vast light-gathering power will be utilized to the full. Under the skillful management of Hale and his enthusiastic and capable colleagues, the confines of the stellar heavens will be enormously extended, and secrets of evolution of the universe and of its structure no doubt revealed. In all the mountain stations hitherto established, as the Lick Observatory at 4,000 feet, the Mount Wilson Observatory at 6,000 feet, the Lowell Observatory at 7,000 feet, the Harvard Observatory at 8,000 feet, and Tenerife and Etna at 10,000, Fujiyama at 12,000, Pikes Peak at 14,000, Mount Blanc and Mount Whitney at 15,000, the researches that have been carried on have fully demonstrated the vast advantage of increased elevation in localities where climatological conditions as well as elevation are favorable. Nevertheless, only 1/2 of the extreme altitude contemplated by Sir Isaac Newton has yet been attained. Can the greater heights be reached and permanently occupied? Geographically and astronomically, the most favorable located mountain for a great observatory is Mount Chimborazo in Ecuador. Its elevation is 22,000 feet, and it was ascended by Edward Whymper in 1880. Situated very nearly on the Earth's equator, almost the entire sidereal heavens are visible from this single station, and all the planets are favored by circumzenith conditions when passing the meridian. No other mountain in the world approaches Chimborazo in this respect, but the summit is perpetually snow-capped, exceedingly inaccessible, and the defect of barometric pressure would make life impossible up there in the open. Only one method of occupation appears to be feasible. The permanent snow line is at about 16,000 feet, where excellent water power is available. By tunneling into the mountain at this point and diagonally upwards to the summit, permanent occupation could be accomplished at a cost not to exceed $1 million. The rooms of the Summit Observatory would need to be built as steel caissons and supplied with a compressed air at sea level tension. The practicability of this plan was demonstrated by the writer in September 1907 at Cerro de Pasco, Peru. A steel caisson was carried up to an elevation exceeding 14,000 feet. Patients suffering acutely with mountain sickness were placed inside this caisson, and on restoring the atmospheric pressure within it artificially, all unfavorable symptoms, headache, high respiration, and accelerated pulse, disappeared. There was every indication that if persons liable to this uncomfortable complaint were brought up to this elevation, or indeed any attainable elevation under unreduced pressure, the symptoms of mountain sickness would be unknown. Comfortable occupation of the highest mountain summits was thereby assured. The working of astronomical instruments from within airtight compartments does not present any insurmountable difficulties, either mechanical or physical. Since the time these experiments were made, the Guayaquil-Quito Railway has been constructed over a saddle of Chimborazo at an elevation of 12,000 feet, and only 6 miles of railway would need to be built from this station to the point where the tunnel would enter the mountain. Only by the execution of some such plan as this can astronomers hope to overcome the baleful effects of an ever-mobile atmosphere and secure the advantages contemplated by Sir Isaac Newton in that tranquillity of atmosphere which he conceived as perpetually surrounding the summits of the highest mountains. In Russell's theory of the progressive development of the stars, from the giant class to the dwarf, an element of verification from observation is lacking, because hitherto no certain method of measuring the very minute angular diameters of the stars has been successfully applied. The apparent surface brightness corresponding to each spectral type is pretty well known, and by dividing it into the total apparent brightness, we have the angular area subtended by the star, quite independent of the star's distance. This makes it easy to estimate the angular diameter of a star, and Betelgeuse is the one which has the greatest angular diameter of all whose distances we know. Antares is next in order of angular diameter, 0.043 seconds. Aldebaran 0.022 seconds, Arcturus 0.020, Pollux 0.013, and Sirius only 0.007 seconds. Can these theoretical estimates be verified by observation? Clearly, it is of the utmost importance, and the exceedingly difficult inquiry has been undertaken with the 100-inch reflector on Mount Wilson, employing the method of the interferometer developed by Michelson and described later on, an instrument undoubtedly capable of measuring much smaller angles than can be measured by any other known method. Unquestionably, the interference of atmospheric waves, or in other words, what astronomers call poor seeing, will ultimately set the limit to what can be accomplished. But even if, says Eddington, we have to send special expeditions to the top of one of the highest mountains in the world, the attack on this far-reaching problem must not be allowed to languish. End of chapter 22.